Hello, this is Jiacheng. I'm going to present GraphGPT-o, Synergistic Multimodal Comprehension and Generation on Graphs. This is a joint work done by Yifang, Bowen-Jin, Suiding, Chaoyita, and Jiawei Han. So first, a little bit introduction. What is multimodal attributed graphs? It can be widely observed in real world. It can be nodes in multimodal attribute graphs are represented by multimodal attributes. It has visual and text modality. For example, in product graphs, it can be a book that is connected with the backpack that is purchased by the same customer and has both the visual attributes and the text attributes. For example, in the domain of art, it can be the artwork done by the same artist, so they can connect it to a graph network. And certain features are challenging to convey through specific multimodality alone. For example, Bluetooth is identified only through text. Black is recognized only through the image, and bought by the same user is inferable only through graph structure. So our task here is trying to do an image text pair generation for node from multimodal attribute graphs. It has many applications. For example, in e-commerce, it can be used for generative recommendation. A user is interested in the phone enters and what new product the user is interested in looking at. It has also has application in art. For example, visual arts, how will a picture titled "A Man Playing the Piano" looks like with 15% Monet style and 50% of Van Gogh style. And the input could be a graph with multimodal attributes and the neighbors of the target nodes on the graphs, and the output could be the text and image generation pair of the target node. And we have several existing works. For example, graph as conditions for generation. It has work called by instruct graph to I, which we have a training setup, and we have used a personalized page rank to do a neighbor sampling and search for the semantic relevance through similarity-based ranking, and put it into an image encoder, for example, clip, and use the GraphQL format to aggregate the graph prompt and to aggregate the modality information. In previous, the instruct G2I model only has an image generation and text condition. For ours, we have image text generation and no text condition. And for LLM for graphs, we have the another one which we have the input graph as a language description and or input graph as a soft prompt. The difference between these two are these are tag text attribute graphs on LLM only text modality. Ours, we are multimodal graphs on multimodal LLMs. And one backbone for our work is about the Dream LLM, where it's a multimodal LLM that can do a text image pair generation. It uses a large language model backbone and use a special token, Dream token, to project into a diffusion model and use it to generate the image, and where the image is further being considered as a condition for next token generation. And here is our methodology. So we are facing a challenge: how can multimodal attribute graphs to be incorporated into multimodal LLM? So for graphs, we are there is no such order, and like in natural language stuff. So first challenge is how to linearize the graph token. Second is how to do the graph hierarchical tokenization. And we design two modules. First is the graph linear tokenization, which we use two text and image encoder. We first do a PPR, personal page rank, to sample the neighbors and choose the modality and choose the order, and also choose the number of neighbors as well, and we use a text encoder and an image encoder to get a text token and image token for both modality of the samples. And for graph hierarchical tokenization, in order to fusion the modality, we design another feature QFormer, which has a self-attention module and cross-attention module, and we do a graph structure QFormer to fuse the neighbor tokens with the nullable tokens, and that we after that we have a uh, node tokens which we can put forward to the uh, multimodal LLM. And for a graphlinear tokenization, we choose a several choice of modality. We use either only image I or token I, or both. For neighbor modality order, it can be image I, text I, image I1, text I1, or we put all the images of neighbors first, and then text of the neighbor first. Of course, for a number of neighbors, we are free to choose. And here is the basic thing. What do we just talk about? We have a learnable token for the modality fusion QFormer, and a frozen text and the image encoder to extract the modality attributes for each node, and align the to align the graph structure for node sequence. We have the graph structure QFormer to align with neighbors in the central node. And for inference, we have this is our prompt about or instruction given a related image and titles of artworks. Image I, text I, please generate the image and title of the target artwork. And input put that into the multimodal LLM. We have the generated image tokens and the generated text tokens, and we can either parallel generate the text and image, or we can use the one as a condition of the other one. So in order, then we have the samples put outside and put on the right side with the generated image or the generated text. And here is our data set. We choose the Art 500K, where the nodes are artwork, ages are the same author, same genre relationship, text as the title, and image is a picture. For Amazon, the nodes are products, ages are co-view relationship, title is the text modality, picture is the image modality. And we use the clip I2, perplexity, clip IT, and the KO divergence as the metrics to evaluate the performance of the model. And here is our experiments. And graph linear tokenization quantitative results are shown in the table. For modality, we try text only, image only, text and image interleaved. For order, we choose text first, image first, or interleaved. For inference, we choose text first, image first, or parallel. And it shows that more modality information tends to enhance the performance. Text first supervision during inference can lead to better alignment with neighbors. And for the quantitative results for the graph hierarchical tokenization, our GraphGPT-o consistently perform better than the original backbone like DreamLM and the fine-tuned version in terms of the perplexity, clip IT, and the KO divergence. And some qualitative results that compare with ChatGPT 4.0, DreamLM, and Ground Truth. So our GraphGPT-o model demonstrate more consistency with ground truth and sample neighbors in terms of the style, the genre, and the characters. And here is another results in terms of the samples. And we're also trying to do the ablation study where we want to see if the sampling strategy would impact the quality of the generation. It sees that personalized PageRank effectively captures the neighbors that are more similar with the graduates compared with neighbor sample and random sampling. And both the graph structure Q-former and the no-feature Q-former contributes a lot to the overall performance in our impact of these two different modules, graph structure Q-former and then no-feature Q-former, in terms of clip I2, perplexity, clip IT, and then QL divergence. And generation with partial target, no feature guidance, the style and the character information is also well captured and through partial no features guidance. Some observation study of the number of samples, number of neighbors. We saw that incorporating information from more neighbors can improve the performance as well. So a few takeaway that we propose GraphGPT-o, a multimodal LLM tailored for comprehensive understanding and creation. Our approach effectively addresses key challenges related to graph topology and the multimodal attribute integration. Some future work could be scaling to larger graphs, handling heterogeneous graphs, and exploring more diverse modalities. Thank you.